Hello everyone. Going to be walking you through some information regarding nervous tissue today. We're going to be talking about resting potential, local potential, and also action potential. Here's my construction of my nerve tissue. I'm sorry, this is a very ripe avocado. I'm going to throw it away after we're done, but I figured it would just be good to construct this nervous tissue out of. We also, right here we have, oh, I'm sorry, see, starting from the top, we've got some dendrites hanging off the side. We also have the soma nucleus. We also have the axon hillock right here, and then we also have the axon moving all the way to the arboration. Let's go ahead and let's talk about this guy. So we've got the dendrites right here. We also have a diagram, a close-up diagram of the dendrite cell. It's packed with sodium and protein pumps, or I'm sorry, potassium and sodium protein pumps. We've got all of the, the positive sodium charged ions out here, and all of the potassium positive charged ions in here. We do have some negatively charged proteins in here. However, that's not a big deal. The ECF is a positive charged environment, and the ICF is a polarized charged environment only because of the negatively charged proteins. Now, the sodium pumps, it's their job to pump the sodium and the potassium ions in and out on a daily basis or continuously in order to make sure that the ICF has a natural resting point of negative 0.75 millivolts. That's what the proteins do. That's their job. They facilitate this action via ATP, moving the cells or moving the ions in and out of the cell. Now, the dendrites want to be at that resting state all the time, just in case something comes along, such as a stimulus. So let's go ahead, let's get on to the resting state right now. So the resting state, so this is achieved when a negative 75 millivolt charge is actually achieved by the inside of the cell membrane. We can actually see the potassium, potassium and also the sodium gates have been completely closed. This cell right here, this dendrite, is completely at rest right now. And so he's just kind of chilling out. He's just kind of waiting. I kind of picture this like a baseball player, just stepping up to the plate, not yet swinging at any pitches yet, just waiting for that first pitch to come. Okay. However, once that baseball player sees that first pitch and he knocks it out of the park, it's kind of like when a stimulus comes into play. This is a drawing of a chemical stimulus interacting with the dendrite. Now, what happens is that sodium gate is going to open, allowing a flood of sodium, positively charged sodium ions to enter the ICF from the ECF. Now, all of those positively charged ions are going to get together and they are going to make a significant charge. Now, this is actually going to create a positive charge instead of a polarized charge within the ICF. Now, if that charge gets big enough, it can move from the dendrite all the way through the soma and down to the axon hillock. Hopefully, hopefully that happens, but it doesn't always happen, just because if it turns out that what's the word? Oh, yes, I'm sorry. So everything that's happening right here and now, creating the positive charge via all of the positively charged sodium ions, that is known as a local potential. Local potentials are not set in stone. They can fizzle out if the stimulus ceases. So that charge could make it all the way from the dendrite to the axon HELOC. However, if the stimulus stops, then the entire process stops. I like to think of it this way. If you're hanging out with some friends and you're at a dinner party, and then all of a sudden you're having a good time, and then all of a sudden the electricity goes out. Well, that's kind of a party killer. It's kind of a mood killer. So that's my understanding of how a positive charge can come together, and it can start to move through the dendrite and through the soma, and then all of a sudden the lights go out. Which means that or in translation, the stimulus ceases to be, and therefore the charge ceases to be. So the only way that a local potential can develop into something more is if it reaches the axon HELOC. Now, when and if that charge is strong enough to get from the dendrite to the soma, all the way through the soma, and then into the axon HELOC, that's where the change can really happen. Because right now, as you can see right here, based off of this graph right now, we've got negative 70 millivolts. This is at the resting state. This is also that local potential right here. Now, we also have a threshold of negative 75 millivolts, which it's kind of getting close to the zero mark. However, it's still negative 75. That is the threshold. Now, if this charge gets all the way to the axon HELOC, that is kind of a game changer. So you're right here, if it reaches the zero barrier, the 0 millivolt line. Now the sodium gates open, and a flood of sodium from the ICF crushes into the crushing into the ICF. And this is where the charge can really start to take off. This is where it starts in the dendrite, and then it moves to the soma. And if the charge is strong enough, it can reach up to 35 millivolts. And then that's the peak of where it can get. Now, the charge can get to the axon HELOC. The interesting thing about the axon HELOC, along with the axon in general, is that there's actually 7 to 10 more times the amount of sodium and potassium gates along in that axon HELOC and through the rest of the axon. So that charge, if it makes it to that stage, it can get supercharged even more. And it actually can start moving faster through the axon HELOC all the way to the arbitration until its end goal. So that is covering resting potential, local potential, and also action potential. Hope you guys enjoyed it. I'm going to throw this thing away. Have a good one.